Now, obviously, when I have broken up the function into its components, I need a reconstruction frame as well. That is, I need to know how to recover the signal and what kind of functions, synthesis functions I require to reconstruct my signal from the broken up components. And that is where we have what is known as a dual or a reconstruction frame. The dual frame is also a frame, right. So, the same frame definition applies, but it is a special frame, it is a dual of some other frame. So, that is why we have a reference frame here. Suppose gamma is the frame that I have used to break up A and B, then there exists a dual frame gamma n tilde, again n could be finite or infinite such that for any function in the Hilbert space, I can write this function as a synthesis equation here. That is, the inner products of f with the analyzing frame or the frame reference frame gamma are being used to reconstruct my f, but then I have another equation here and we will talk about that very soon. So, let us see what this dual frame has to satisfy. The dual frame has to satisfy once again a frame condition, but because it is a dual frame, the bounds for the dual frame should be related to the bounds of the reference frame. So, we have gamma as a reference frame and gamma tilde as a dual frame. A dual frame is also a frame, therefore, a frame condition exists, but it is a dual of something. So, that something will determine what bounds I should get here, and A and B here are the bounds on the reference frame gamma. Now, let us get back to equation 4. What this tells me here is I could switch the roles of gamma n and gamma tilde. What this statement, this result says or theorem says is that I can use gamma for analysis and gamma n tilde for synthesis, or I can use gamma tilde n for analysis and gamma for synthesis. Either way, I can switch the roles, they are just duals of each other. So, you do not have to use one specific, necessarily one for analysis, gamma for analysis and gamma tilde for synthesis. You can switch their roles, and that is where they are duals of each other, and that is what this equation means. If I use gamma and tilde for analysis, I can use gamma for synthesis. That is what it means, right. That is a very interesting thing. And again, you have to keep telling yourself that a frame is nothing but a collection of functions that I am using for analyzing and recovering a signal. Now, what is this dual frame? The dual frame is given by this expression here. Now, do not get scared looking at this expression. This u that you see here is called an operator, but you can also imagine u to be a matrix. What does this u do? It essentially operates on f, or it multiplies with f and produces the coefficients that you are computing. So, essentially you are rewriting the inner product as a matrix multiplication with a vector, that is all. And if you can think of u as a matrix, then u star u inverse is just an inverse of the product of u star, which is a complex conjugate of u, because your gamma n's can be complex valued also. Therefore, u could be complex valued and u star denotes a complex conjugate. So, you take u star u inverse times gamma n. That is what will get you gamma n tilde. What this means is all I need to do is choose gamma and then the dual frame gets fixed, or choose gamma n tilde, the other frame gets fixed. So, I do not have to really search for another set of functions that will help me recover the signal. Now, if the frame is tight, there is a nice recovery expression from here that that is when A equals B, you can show quickly that gamma n tilde is 1 over A gamma. Now, this proof I avoid, you can refer to Mallet's book or any literature. It is a fairly easy proof, very simple proof, but in the interest of time I am just avoiding it. So, when the frame is tight, the dual frame is simply 1 over A gamma n, or the dual frame function. What this means is my recovery expression simplifies to this. All I do is in my gamma n, for my gamma n tilde, I substitute 1 over A gamma, and then I get f equals 1 over A sigma, this inner product of f with gamma and gamma itself, that is it. So, obviously what this means is when the frame is orthonormal, any orthonormal frame is a tight frame, but any tight frame is not an orthonormal frame, right. So, if A equals B equals 1 further, then what happens? The reconstructing frame functions are the same as the analyzing one, or I mean if you think of gamma and tilde as a reconstructing one. So, the dual frame is the same as the other frame itself, they are identical. Therefore, the recovery expression becomes very simple, as we will see later on. So, let us quickly move on to wavelet frames now. Why did we study frame theory? Because we discretized CWT. When we discretize CWT, we are breaking up the signal f or the function f onto a family of wavelets evaluated at specific scales a naught to the m and translations n b naught times a naught to the m. Frame theory allows us to now comment and qualify on whether this breaking up of the signal onto this bunch of wavelets that I have obtained by discretization yields any sensible representation or not. Now, you can think of Fourier frames, you can think of any frame, your gamma could be anything. Now, my gammas are wavelets, right. So, wavelet frame results essentially when a CWT is discretely sampled in scale and translation. So, this discrete is not DISCREET, that means something else in English. So, this is DISRETE. So, discrete is sample in scale and translation parameters, and the A naught and B naught should be chosen such that this frame condition is satisfied for the wavelet coefficient. So, your T of m comma n is nothing but your inner product of the signal f with the discrete wavelet at scale m or scale A naught to the m and translation location n. So, you ideally what now this frame theory tells me is I should choose A naught and B naught such that I get a frame, because only frames will allow me to produce stable representations. This energy condition essentially means that I have stability in my representation. So, that is the thing. If you look at it other way around or intuitively, I should choose my A naught and B naught. So, if you look at the figure that we had, the A naught and B naught will determine the grids on scales and translations. I should choose my A naught and B naught in such a way that the entire time frequency plane. So, now I have time and omega. Whenever I choose a particular wavelet, what I am trying to do is I am trying to capture the signal in some box here. These are, as you know, Heisenberg boxes with sigma t and sigma omega for that wavelet, right. And as I move into the high frequency regime, I have these boxes. So, as I am choosing different A naughts and B naughts, what I am doing is I am tiling the time frequency plane. Now, I should choose my A naught and B naught in such a way that the entire time frequency plane is covered. I want to make sure that there is no gap in this tiling. That is, you are a mason, you are laying down tiles on a floor, you should choose your tile widths in the 2 dimensions in such a way that there are no gaps. Not only tile widths, but the spacing between tiles. You are allowed to have overlapping tiles, but not tiles with gaps, and that is what essentially frame theory is allowing to you to mathematically determine whether there are gaps, right. That is the key point about frames. Now, I would like to choose, I can have tilings like this, and likewise I can have tilings like this, but when I choose A naught and B naught such that there are no gaps between these tiles, CWT does this, but in DWT now I have the opportunity of choosing A naught and B naught such that there should be no gap. So, when I do not have any gap, then these boxes do not overlap. Then what I would have is a tight and orthonormal frame also. Okay, orthonormal means tight. So, that is the key. I can choose overlapping tiles, I can choose non-overlapping tiles. There is a provision for both. So, I hope you understand what we mean by spanning the time frequency plane. So, what is the requirement on discretization? This was a fundamental result by Dobischi who showed what conditions are required to generate a wavelet frame. In other words, there should be no gaps in the tiles. It turns out that any family of wavelets that you obtain by discretizing, this should not be j comma n, this should be m comma n. Any family of wavelets that you obtain by discretizing the scale and translation will give rise to a stable representation or a frame in the two-dimensional real space if and only if the frame bounds satisfy this. So, it is C psi is the admissibility constant, you know that. B naught should be A naught here, B naught and A naught should are your user defined parameters. Put together there should be two constants A and B that you can always find. Now, you know for example, Monlet wavelet does not have a finite C psi strictly. So, a Monlet wavelet, whatever you do discretize, you will never be able to find A and B, therefore, it can never be used for DWT. That is why earlier in CWT we learned that Monlet wavelet cannot be used for DWT.